So we can continue. Let me record. Those things, dynamic array offers a way, or a dynamic way to have a list that can always have a reserve space to add on our arrays. If a user continues to append element to a list, any reserve capacity will eventually be exhausted. In that case, the class requests a new large array from the system and initialize the new array so that it prefix matches that of the existing smaller array. At that point in time, the old array is no longer needed, so it is reclaimed by the system. Intuitively, the strategy is much like that of a hermit crab. We give empirical evidence of the Python list class based upon the strategy with the source code fragment code 5.1. In this system, we import a modular system ASS provided, which will help us to get the size of the function. And then we declare empty data list, and then we run the for loop, search for n number of numbers we want, and then we declare A as the length of the data, how long is the data, and then B, that's where we get the size of the strings, actually size of the bytes. Then we print the length of from 0 to 3, it takes a byte, then data append to 9, we don't append to it. So if you know the size is 72, and then it jump from if you want 220 size of bytes, you can see how the dynamic help here. It create from 0, it has a 2 bytes. If it's 1, it jump from 70 to 104. If it's 2, it remain at 4. But if it's 5, it jump to 136. Continue, etc. In evaluating the results of the element, we draw attention to the first line of the output. On the fragment count of 5.2, we see that an empty list instance already requires a certain number of bytes of memory on our system. In fact, each object in the Python maintain some state, e.g., a reference to denote the class to which it belongs, although we cannot directly access private instances variable for a list. We can speculate that some form it maintains the state information akin to it. We have these numbers. Reference current allocated to array initially at 9. I think here is explain how that program runs. The implementing a dynamic array, although the Python list class provides a highly optimized implementation of dynamic array upon which we rely for the remainder of this book, it is instructive to see how such classes must be implemented. The key is to provide means to grow the array as A that stores the element of a list. Of course, we cannot actually grow that array as its capacity is fixed. If an element is appended to a list at a time, when the underlying array is full, we perform a following steps. Allocate a new array B with a large capacity. We set it A of I to A of I, B of I to A of I for I 0 till n minus 1, where n denotes the correct number of items. So set A B to B, that is, we henceforth uses B as an array supporting the list. Insert a new element in the new array. This is A, this is B, which is empty with a double number of indexes or capacity. We take A list, we put it on B, we still have a space. So it gives us a way to operate. If there's something we want to add more, we still have a space of at least 4 feet. Illustration of the 3 steps for growing a dynamic array A, we create a new array B, and number two, we store an element of A in B, and then C, we reassign a reference A to the new array, not shown in the future cabbage collection of the old array for the insertion of the new element. This is where we just in a code we run whatever we did in that previous one. Running array, you create a class dynamic array. We initialize the constructor with a self method self dot private n is 0, self dot private capacity rate 1, declare array capacity. It runs. It just as I was explaining in that illustrated way. The immortized analysis of dynamic arrays. In this section, we perform a detailed analysis of the running time of operation. On the dynamic arrays, we use the big omega notation introduced in the previous section to give an asymptotic lower bound on the running time of an algorithm or steps within it. The strategy of replacing an array with a new larger array might at first seem slow because a single append operation may require the big omega of n, which is linear time to perform, where n is the current number of elements in the array. However, notice that by doubling the capacity during an array replacement, our new array allows us to add an n new element before the array must be replaced again. In this way, there are many simple append operations for each expensive one. This fact allows us to show that a performing series of operations on an initially empty dynamic array is efficient in terms of total running time. Using an algorithm design pattern called amortization, we can show that performing a sequence of such append operations on a dynamic array is actually quite efficient. To perform an amortized analysis, we use an accounting technique where we view the computer as a operated appliance that require payment of $, a constant amount of computing time. When an operation is executed, we should have enough $, available in our current bank account to pay for that operation's running time. Thus, the total amount of $, spent for any computation will be proportional to the total time spent on that computation. The beauty of using this analysis method is that we can overcharge some operation in order to save up $, to pay for others. You can see that it grows in a exponentially start from 1, and then have 2, and then for 2, then from 4 is a geometrical progression, and then for 16. Then the time of a series of append operation on a dynamic array proposition set, well, let's SP a sequence implemented by the means of dynamic array with initial capacity 1, using the strategy of doubling the array size when full. The total time to perform a series of an n append operation in S, starting from S being empty, is the big O of n, which is linear. Justification lets us assume that $1 is enough to pay for the execution of each append operation in S. Excluding the time spent for growing the array also lets us assume that growing the array from size k to size 2k require k $, for the time spent initializing the array. We shall charge each append operation $3, $3, thus overcharging each append operation that does not occur on overflow by $2. Fortunately, this $, can be found stored in a cell 2 to the power of I minus 1 through 2 to the power of I minus 1. Note that this previous overflow occurred when the number of elements became larger than 2 to the power of 1 to the power of I minus 1 for the first time. Whereas the subatomic stored in cells 2 to the power of I minus 1 through 2 to the power of I minus 1 has not yet been spent. Therefore, we have a varied amortization scheme in which each operation is charged 3 $, and all the compensation time is paid for. That is, we can pay for the execution of n appending operation using the n 3 times n $. In other words, amortizing running time of each append operation is constant, the peak O of 1. Hence, the total running time of n operation is linear, peak of n. Here also they talk about the same thing, geometric increase. Although the proof of proposition 5.1 relies on array being double each time, we expand the peak of one constant time amortized the bound per operation can be proven for any geometrical increase proportion of an array size. When choosing the geometric base, there exists a trade-off between runtime efficiency and the memory usage. With a base of 2, in doubling the array, if the rust sensation causes a resize event, the array essentially ends up with twice as large as it to be. If the instance array, if the instant array, if the instance increase the array by a quarter or only 25% of its current size, in essence, a geometric base of 1.25, it do not risk wanting as much memory in the end. This is still proved to be a constant time or constant function running time on meters bound using a constant factor greater than the 3 $, per operation. Beware of arithmetic progression. To avoid reserving too much space at once, it might be tempting to implement a dynamic array strategy in which a constant number of additional cells are reserved each time an array is resized. Unfortunately, the overall performance of such a strategy is significant. It's an extremely an increase of only one cell causes each append operation to resize the array into the formula of 1 plus 2 plus 3 plus into 2 plus n summation, and give us a omega of 2 squared, which is quadratic overall cost. Using an increase of 2 or 3 at a time is slightly better as portrayed in figure 5.3, but overall cost remains quadratic. This is also another example of performing series of n append operation on initially empty dynamic. Memory usage and shrinking an array. Another consequence of the rule of geometric increase in capacity when appending to a dynamic array is that the final array size is guaranteed to be proportional to the overall number of elements. In essence, the data structure uses a linear runtime memory. This is a very desirable property for data structure. If a container such as the Python list provides the operation that causes the removal of one or more element, criteria care must be taken to ensure that the dynamic array guarantees a linear memory usage. You can calculate the time spent on those using the simple start from time, giving the time module, running a for loop, append or add, then running the time. Technically, the time elapsed between the start and end includes the time to manage the iteration of the for loop. In addition to the append calls, the empirically run a result of the experiment for increasing the likely value of n as shown in the table 5.2. Running n with a milliseconds, say to put n100 run of a millisecond of 0.2 219. If it's 1000, it it goes upside and down. So 1.6, and then here 1.164, 1.15. It is 10 million, 1.1.5. So it goes up and down, and also as more as you have more ends, seems like we're going down on a space on a runtime or elapsed time. The efficiency of Python sequencing types, Python list and table classes. The non-mutating behavior of the list classes are precisely those that are supported by the table classes. We know that the tables are typically more memory efficient than the list because they are immutable, and therefore there is no need for any underlying dynamic array which supplies capacity. We summarize the associative efficiency of the non-mutable behavior of the list and table classes. The operation length of data, it goes content, and then the data in J also goes constant time. Data count, it goes in linear. It goes in K plus 1. Value in data, a for loop, or a loop on some sort, it goes also in K into 1, etc. The asymptotic performance of the non-mutating behavior of the list and table classes. Identifiers such as data 1, data 2 designate the instance of the list or table classes, and N1 and 2 enter their respective length for the containment checks index method. K represents the index of the leftmost occurrence with K assigned to N if there's no occurrences. Constant sum operation, the length of an instance is written in a constant sum because an instance explicitly maintains such this information. The constant sum efficiency of syntax data into J is assured by the underlying access into an array. Searching for occurrence of a value, each of the account index and the contain method proceed through iteration of the sequence from left to right. In fact, in our first code, they were estimated how those behavior might be implemented. Notably, the loop for computing the count must proceed through the entire sequencing, while the loop for checking containment of an element or determining the index of an element immediately exits once they find the leftmost occurrence of the desired value. The graphic comparison between the two sequences are defined lexicographically, defined in ascending order, A, B, C, D. The worst case, evaluating such conditions requires an iteration taking time proportionally to the length of the shorter of the sequence, because when one sequence ends, the lexicographical result can be determined. However, in some cases, the result of the test can be evaluated more efficiently. E.g., if evaluating the length, the list of 7.3 list, and then is less than 7.5, it is clear that the result is true without examining the remainders of those lists. Creating the new instance, the final three behavior of table 5.5, 5.3 are those that contract a new instance based on one or more existing instances. In all cases, the running time depends on the construction and initialization of the new result. Therefore, this asymptotic behavior is proportional to the length of the result. Therefore, I find the slice of data 6 million to 6 million and 8 can be contracted almost immediately because it has only 8 element difference. While the slice data of 6 million to 7 million, it has 1 million element difference. Thus, it's more time consuming to create. The mutating behavior, the efficiency of the mutating behavior of the list class are described in table 5.3. The simplest of those behavior has a syntax of J of data into J assigned to variable or value, while and is supported by the special set item method. This operation has a worst case of peak of 1, which is content time running behavior, because it simply replaces one element of a list with a new value. No other element are affected, and the size of the underlying array does not change. The more interesting behavior to analyze are those that add or remove the element from the list. Yeah, this is where we're checking of our contents. Adding an element to the list in section 5.3 fully explore the append method. In the worst case, it requires the peak omega of n linear time because the underlying array is resized, but it uses the peak of one constant time in the amortized sense. This also supports a method with a signature insert built-in method k into value. That insert giving the value into the list as at index 0 is less than or equal to k is less than or equal to n, while cheating all the subsequent elements. Here we're running a function insert self contractor and then k value and then the terminating value. If n is equal to capacity, we find is it enough room? If not, so we do if not, then we do a double capacity, and then we shift to the left, and then we shift to the left, the right mode first, and then we create a new one. And this way, the diagram where you run that function. Removing the list. Python list has a built-in call or method which is say pop, and then that list eventually removing the last element of the list. This is more efficient because all other elements remains in their original location. This is efficiently content time operation, but the bound is almost because Python will occasionally shrink the underlying dynamic array to conserve the memory or to save the memory. Parameterized version of pop of k remove the element that is at index k is less than n of the list, shifting all the subsequent element leftward to fill the gap that the result from the removal. The efficiency of this operation is big O of n minus k, as the amount of shifting depends upon the choice of the index k. Note that this implies that the pop of 0 is the most effective call using the peak omega of n linear time, which the pop of 0 is the first element. So the pop start from the end. So you must go from here, go back until it reaches 0. So it will take its time. That's why it's the most expensive call. Right. Another better way to remove this one, you just give it a score and remove. See if you want to remove 1, if you want to remove 2, just give it this value. Okay, I'm going to remove this value that is index 2. So it's much more efficient compared to the pop if you want to take out the first value. Extending a list, Python provides a method named extend that is used to add all elements of one list to the end of the second list. In effect, a call to data.extend other produces the same element, same outcome as the code for element in other data.append element. In either case, the running time is proportional to the length of the other list and amortized because the list array for the first list may be resized to accommodate the additional element. In practice, the extend method is preferable to repeated calls to appended because of the constant factor in the osmotic analysis are significantly slow. The greater efficiency of extend is threefold. First, there is always some advantage to use appropriate Python uh, methods which are built in, because those methods are often implemented natively in a compiled language rather than interpreted Python code. Secondly, there is less overhead to a single function calls that accomplishes all the work versus many individual function calls. Finally, increasing the efficiency of extend comes from that resulting size of the updated list can be calculated in advance. If the second data set is quite larger, there is some risk that the underlying dynamic array might resize multiple times when using the repeated code to append. Contracting the new list, there is several sensitivities of contracting new list. Almost all the cases, the asymptotic efficiency of the behavior is linear in the length of the list that is created. However, as the case in the preceding discussion of the element, there are significances in the practice efficiencies. We've did what you call a list compression, which is a shorter way of operating the for loop with just one line. Square assigned k by 10 for k in range 1 plus n plus 1. This is much more faster using the list convention, this method, than compared to declare an empty square and then run a for loop. A pattern function, a pattern matching, some of the most interesting behavior from an algorithm point of view are those that in some way depend on finding a string pattern within a larger strings. This code is the heart of methods such as container, find, index, count, replace, and the splits. Strings algorithm will be a topic of the next chapter, which is chapter 30. This particular problem, known as the pattern matching, will be a naive implementation runs in the peak of m times n case, because we consider n minus n plus 1 possible starting indexes for the pattern, and we spend the peak of m time at its starting position, checking if the pattern matches over. We develop an algorithm for finding a pattern of length m within the longer string of the length and in the peak of n time. Composing the strings using the for loop document. Most of the time when you're using a for loop, a nested loop will give us a quadratic runtime. So it will be inefficient code of time to spread in Python, perhaps because of the somewhat natural appearance of the code and mistaken presumption about how the plus equal to assign operator is evaluated with strings. Using array-based sequencing, during the course of the game, the first application is started as a starting sequence of the high score entries of a video game. This is a representative of main application in which a sequence of objects must be stored. You could just easily have choose the store record for patients in a hospital or the names of players on the football team. Nevertheless, let us focus on the storing high score entries, which is an application that is already rich enough present some important data structure. This is the game that they're talking about, replacing one entry of a list high score. We define a constructor in it with a self without name, score, value, and then we define self-method name assigned to score assigned to name, And then we define a method assessor, which is get the name, return the name, get the score, return the score. And then a string, we return the string, the first string, and then the second string with the format, which is will be the name and the score. The class for high score maintaining the sequence of high score developer of the scoreboard. We're given a index 0, which Mike has a high score 1000, and then check is the last one. Running that score, we have a class called a scoreboard fixing the length sequence of the high score in a non-decreasing order. And then we have a contractor in it with the method capacity at 10, with top 10, initialize the score within the given maximum capacity. We give the store to 9 times capacity, it doesn't increase. Assign to first 10. We get item self at key, reserve the states of the future score. And then we're returning the strings representation of the high score list, considered adding entry to the high score. Does the new entry qualify as high score? Answer is yes. If the board not full or score is higher, and then you put the last entry. That's why we're running adding Chile 740, which is above Paul. We have insertion sort algorithm, which is insert input an array of an n-comparable item, output an array of an element arranged in a non-decreasing order. We run a for loop. Simple cryptography and illustrating application of a strings. The list is cryptography of secret message and their application. This field studies ways of performing encryption. It takes a message called plain text and converts it into a scrambled message called a ciphertext. Likewise, cryptography also studies the ways of performing decryption. Takes cipher a secret text make it into the plain text. We generally run from the strings to character list. I think there's where they run. Okay, there's the class state mean. Caesar cipher. They called Caesar because apparently it was inspired by Caesar in his empire, where he was hiding the message into his enemy. And then we create a method called self and shift variable encoder with the 26 of the alphabet, decoder with the 26 of the alphabet running k into range of 26 between the alphabet of 26. And then it's a standard code to character and shift to shift to 26 from A to what to Z. And then decoder we shift from K from A to from Z to K to A. And then we set forward, join the decoder and then backward join the decoder. Then encryption of the message. We transform the message forward, then described message secret. We return the described message which has been given as a secret one. Then we run where we transform those message where we decipher those messages, and then we call the main to the first which is to decipher this message with the eclipse in the brain, meets at tools, and then they call it encrypted message, which is message, and then we print the coded one, and then we decipher it. Highlights of a multi-dimensional data set. Multi-dimensional data set is kind of matrix, we call it matrix, where we have a square. This is a two by two matrix. You have a 2 rows and 2 columns. So this is what we call a multi-dimension. Usually we put the data in the column of whatever one we need. That's why we create containing a dimensional. We assign the data to 0, multiplied by C to R. Creating two-dimensional image and positional game. The game of the tic-tac-toe. I think use a three-dimensional, a 3 by 3. That's where you create just create a list, first list, and then put a comma, second list, put a comma, and then the dead list. So you have a 3 by 3, 3 column, 3 rows. That's where they're running this code. I think we have less than 3 minutes. And this is the game being created. So in case maybe we can just do this exercise for this end of the chapter. Maybe we can just do this because of no time. Execute the experiment from the code 5.1. And compare the results. For this code. Okay, let's just give it a number of 50 inputs. And the data, create an empty data. Of K in range, and we'll give it a length of the data. We give the system dot get size of data. Say print size in bytes.